starting, right? So first of all, thanks to the organizers, because I'm an outsider to this community. I come from LHC background, PP Coalition. When I saw this event is happening, I thought, why don't I sit to the talks and learn some what's happening at EIC, what can be done. And as a talk proposal, I thought, since I'm involved heavily in machine learning in LHC related activities, why don't I try to draw a parallel comparison between the two experiments from a broad ML perspective and see where we can exchange information. And that's the whole purpose of this talk. Okay. So when we think of a collider experiment, it can be broadly thought of this program. Like on one direction, we have simulation-based studies where we have an underlying theory in mind. We do physics simulation for that. We do some detector smearing, and then we do some physics inference. And on the other hand, nature is playing some dice, which we don't know. We want to reveal that. We build our great machines. We do the experiments, try to measure the unfolded distribution so that we can do one-to-one comparison with the theories. And then we do a statistical inference and probably try to extract the parameters of our theory, or if there are some unknown physics happening at nature, we try to grab it from our experiments. So that's overall global program. Now, from this bigger perspective, probably you will agree that same set of chains are applicable equally for LHC program, for all its sub experiments like CMS, Atlas, etc. And in EIC, which I don't know about, learning from you, this flow chain is still valid because you will have simulation, you will measure, you will try to do some inference about what's going on. So if we can debug this flow chain into smaller parts and try to see if we can improve our understanding anywhere here using deep neural networks, in that language, we can draw a one-to-one correspondence between LHC and EIC. And probably that's the context in which these two communities can start talking to each other. So that's the motivation for me to come here and talk to you. Okay. Now, those chains of few blocks, those are not simple ones. We really need to expand that up. And if we do that, the whole collider program flowchain happens in the following way. We collide stuff. There is a trigger process because we can't collect all the data which we have. We have a shortage in our storage. Then what we do is like object reconstructions, because finally what we are left with are jets, leptons, missing transverse energy, photons, and stuff like that. So we really need to reconstruct each of those individual objects. Out of those which we reconstruct events, applying several event selection cuts, object selection cuts, and finally we do our analysis using some order statistics. And from a simulation side, we have our matrix element and pattern shower for the Monte Carlos. We run the branching of pattern showers. The event generators are there to do that. Then we have a big program of detector simulation where Gian comes in, because without a realistic detector simulation, we can't have a matching here. And the rest of the flow chain more or less similar. So now we see that given this two broad program of theoretical simulation as well as experimental measurements go side by side, I will try to convince you that ML can play a very major role in each part of this flow chain. And it has already brought improvements and understanding in the tasks we are involved in, different subgroups of LHC physics. And if you look at other experiments, they are also trying to do that. So now if we can identify where exactly in this bigger picture there are similarities between LHC and EIC, and in what context, at least from a machine learning perspective, the tasks are roughly similar. There we can really talk and see where we can help each other. Okay. So let's do a 101 1-minute crash course of what we really do when we say we are doing machine learning. It's like a jargon buzzwords. In the context of colliders, for the time being, let's say this is an equation in which where we input some data. Now, the data format is important to choose how we represent our data, and there where the grid or the images on which we apply convolutional neural network, or if we have sparse data, we use sets or graphs, or there can be trees. So this is our input data. What are neural networks? They are just parameterized functions, nonlinear functions. So we have to choose these nonlinear functions in a way so that they can take input all these data structures. And once we construct this function and feed some data x, we have some output y hat, right? And then we have the usual story of computation of loss function. Now, here, we really need to inject our physics knowledge for each steps of these constructions. Like, given a data which is coming out of our physics measurements, which is the right appropriate representation? What architecture do we choose? We need to inject physics in the construction of our loss function. And then the data can be classified in several stages. Like, depending on whether we have the label or not, or in a real life data, or in a simulation, how well we have our labels reconstructed. Based on that, we can have a supervised learning task where the labels are very well known, and there can be cases of weak supervision, semi-supervision, and in cases of real-life data where we don't have any label, we really need to build methods of unsupervised learning whose sub-branch is something called self-supervised learning. These are also something we are exploring. So we will proceed in this talk that each of our machine learning tasks for the subparts of the experiments, we will try to understand what we are doing in this language. Okay, so that will ease up our life. And once we can do that through the broad sense lens of machine learning with estimation of realistic uncertainties and interpretability, we will see many tasks here are quite similar. So let's do that. Now, when we do that, why I say, in realistic terms, this is the LHC timeline. It will take data until 2041, and the data analysis will go on probably for 5-6 more years. And here is your timeline of EIC. So we see at least like 10 to 15 years of overlap, active overlap of these two communities are there. So there is no reason why these two communities shouldn't talk and exchange their knowledge, okay? And we only have to gain. There is nothing to lose if we do this cross-talking. So I think we should start it from now. Given there's a well-understood LHC physics program, EIC physics program is growing, we can just take this timeline up to this time scale, starting now, and we should talk. So in a fundamental experimental program of particle physics, the basics of the whole program, you can decompose into few tasks. Okay, one is the calorimetry, tracking, object reconstruction and object identification, and the event reconstruction. So I will go through each small steps one after another and try to see where we are applying machine learning. So first is the calorimetry. And the language of machine learning, which I built up in few slides before, calorimetry is the task that we have a segmented calorimeter, both in the longitudinal and transverse direction. We have like sparse energy distribution in the calorimeter. We feed this neural network, feed this data into some of the neural network and try to identify which particle gave this energy depositions, what was the energy of the original particle, and what was its label, classification. Okay, so this is the tasks we are up to. And in the first talk, we learned that there is a technique called jet images, and there, when it was published, people just took that idea and started doing all possible jet images analogous thing for doing machine learning. So what was the task? People realized that the calorimeter shower can be represented as layered images, and if you feed that image into a convolutional neural network, you can perform any supervised learning tasks. So for that, what became popular in the jet substructure community, that they started classifying between two-prong jets versus one-prong jets, and also later extended it to top jets. So here are some early attempts which started. And here I'm showing you, people brought these tasks down to individual particle identification in calorimeter, where you have sparse energy distribution. So for this task, sorry, there were some early success, but in our realistic calorimeter, there are something called sampling fluctuation, where you don't know how much are the proportions of electromagnetic components in a hadronic showers and things like that. Those were yet to be well understood. And then people started modifying and improve their architectures to see whether this can be improved further. Where I and my collaborators came into picture, we were initially interested in shower segmentation. Now, if you look into a hadronic interaction or hadronic jets, most of them are charged pions. So we were interested that if there is a charged pion and a neutral pion flying close by to each other, and they deposit some energies into the calorimeter, how do we segment these two showers? And this is the task first we were involved in. And there we could prove that we can develop fancy neural networks which can really separate these two showers quite well. And in the process, we could really extract the individual energy depositions of calorimeter cells, and this was well established. In the process, we established something called super resolution technique. So what came out as a byproduct of this project is we started asking ourselves that if two particles fly very close by, so that they start depositing energy in a very close proximity region in a calorimeter, how do we ever identify there were two particles and not one? And in the process, we really developed a method called super resolution, where the whole goal was, let's say we make a measurement from a low granular calorimeter. Can we predict the same shower for a high granular calorimeter? And this method was well established. We could establish that we really can reconstruct neutral pion masses using this method. And when I look into the citations which we received, I highlight a few of them. And with not so great surprise, I find that people who are thinking about electron-ion collider have cited our paper. And there are some colleagues of yours who are thinking in this direction, that how well we can predict individual particle shower shapes for a higher granular calorimeter in the context of EIC using this kind of methods. So these are certainly worth venturing. Okay. Once we established this method, we brought this inside Atlas. I'm an Atlas member. There we built a bit more fancy neural networks, because the real life detectors coming from test beam, etc., are kind of a bit more complicated. But there we started solving simultaneously a classification and a regression task. And for that, we again had a dense environment in a real Atlas simulation. And we tried to classify and identify individual pions, both charged and neutral. So hopefully you have seen from the morning enough numbers of receiver operator characteristics, which are called ROC curves, from two of the talks involved jet. Here the classification is between neutral pion and charged pion. And in this plot, this corner of top right is better. And here you can see when we scan over different kind of architectures, graph neural network started giving better performances, because the heterogeneity nature of the showers of a real life detector prefers like the point representation of the data. So GNN worked better. And here we tried to do along in the segments of energy bin, how do we improve single particle identifications? And here is a like demonstration that if you have a charged pion And if you reconstruct only through tracker, with higher energy, the track resolution worsens. And if we apply neural network, we can regain back the energy resolution. So these things are all working in real life experiments. And when we look into CMS, they are also applying certain graph neural network for electron identification. So here you can clearly see improvements in the resolution when you compare to like non-neural network based, like, okay, so BDT is also neural network, but let's say deep neural network versus modern deep learning architectures, we see improvements both in the resolutions, we can see that. So the takeaway message from all these discussions is that all the LHC experiments right now, the single particle IDs are all neural network based, and they will be there forever. I mean, as long as LHC runs, and we can only improve on top of that. And I think when I was browsing the pages of AI for EIC, these are the similar kind of activities which have started. It's just for a real running experiments. You really need to invent day in, day out for the latest architectures to see which one works best. Okay. Now comes tracking, another fundamental like program for any experimental stuff. So here, the core task we try to solve is that in a tracking layer, we all have hits, and the whole tracking program is just connecting these dots. So how well we can connect the dots and not misconnect the dots, that's the whole tracking program. And we ask a neural network to do it. Right. So what turned out to be best in this context, initially people started like 2D snapshots of these hits flying in a 3D tracking volume. They applied CNN-based like reconstruction of the tracks. But right now we have understood like GNNs are the way to go, because these dots are really like some silicon layers in the 3 dimensions. And connecting the dots is the core program of the tracking. So if you represent the dots as a fully connected graph, then the tracking using a neural network, it's a task of edge finding. We really need to find which pair of dots to connect to get the right piece of tracking. And that's what we ask a graph neural network to do. This is an example of the typical architecture we are right now using for a track reconstruction. And these are deployed inside real-life experiments. So the Atlas tracking algorithm using graph neural network is on track. Here is a public plot. You can see for like not so strict criteria using graph neural networks, we have almost 100% tracking efficiency. And if we pre-select the hits using certain filter, then the statistics goes down. So our reconstruction efficiencies of the tracks goes down to 90%. However, GNNs are working, they're working pretty well. And we are having fun in the tracking region, again, using neural network. CMS, although prefers using convolutional neural networks, they have gained like efficiencies up to certain percentage. They have also a public plot for how much is the fake track reconstruction probability, which is the fake efficiency, okay? But again, both calorimetry, where there are particle IDs, and tracking, run 3 onwards will be all neural network based. And there is no reason why this shouldn't be ventured in the upcoming future collaborations. Now comes, at least my favorite project, when you combine calorimetry and tracking, what you have is something called particle flow. So this is global event reconstruction. And what is the task we have in hand? This is a snapshot of, conceptual snapshot of what we measure. Like we have some curvature in the tracks, we have some calorimeter energy deposits. And what we have to do is to reconstruct the truth particles, okay? So this is where like the data representation is a heterogeneous graph, because the trackers have some sorts of features, the calorimeters have some other sorts of features, and you need to put all through a well-trained neural network to get what are the stable particles which probably have given this energy distribution. So CMS people publish something called MLPF. And here is the architecture. I won't go into detail, just to show you that they had like a summary statistics of what their individual identification are for each individual kind of EM and hadronic particle, as well as what are the bulk kinematic distribution. However, their method had some sort of problem where the individual sampling fluctuations were not taken here into account. So that's where we proposed a method. And the conceptual part is that when a particle enters inside a calorimeter, there is shower splitting, and a particular cell of a calorimeter can receive shower segments from different particles because there are multiple particles in the event. And that's why a truth particle fragments into several detector hits. And when you do a reconstruction of the particle flow candidates, you probably want to recombine again all these particles in certain combination to get the reconstructed particles. Okay. And that's where we proposed a new method of hypergraph-based method. The whole concept of hypergraph is that you really don't connect two elements of a set, but there can be multiple elements of a set which can be like clubbed together with one construction called hyperedge. And for a splitted shower, that hyperedge, which really connects all these dots, that should be analogous to a reconstructed particle. So this is the new concept which we implemented. I don't go into the details of the architecture because that's not so much relevant. But the takeaway point is that when we compare to other networks which didn't apply hypergraph, but regular graph neural network, we obtained some improvement. Not a lot, but certainly some improvement. And when we saw individual event displays, we really could address the problem of like how a neutral hadron recoils inside a calorimeter, how much is the sampling fluctuation. This kind of minute experimental details we could really catch through this hyperedge reconstruction. And I'm pretty excited about this idea. Like right now, this has been this is on the process of being implemented inside Atlas, and probably run 4 of Atlas will be using this method wholly. Okay, and this is an event display that given some given the complexity of the event, how many active cells, how many edges and particles we have, we get back the right kind of event displays, which means these hypergraph-based networks are working pretty well. And when I was browsing the pages of EIC in the jets and heavy flavor working group, I saw there are discussions among particle flow. So there are no reasons why you shouldn't bring these kinds of methods inside your particle flow right from now. Okay. Jet tagging. You heard a lot about jet tagging, nothing to repeat, just that the whole program of jet tagging is solving some inverse problem where we start from the energy deposits inside our calorimeter, and we want to infer back what's happening at the center of collision, where we don't even know how to compute exactly the forward function. So we try to model these inverse functions using neural network. The most professional kind of highly cited ones in our community is what is called particle net, but we should mention that particle net idea, which is dynamic edge convolution, was borrowed from this paper by Michael Braunstein and his collaborators. They wanted to classify different geometric objects, and that has been brought in the context of particle physics. Right, this is a snapshot of zoo of all the models people are trying right now. Top tagging, W tagging, it's the whole community swamped with different architectures. Everyone is drawing a rock curve for top tagging. And you already heard a lot about jet tagging from the previous 2 talks. My interest, however, on heavy flavor tagging, because I'm involved in the Charm-Yukawa analysis of LHC. Identifying heavy flavor jets in a better way is my real fun. So what I tried to do, instead of feeding heavy flavor jets into a neural network and asking it to tag, we wanted to reconstruct the secondary vertex inside a jet, just to exploit the physics of heavy flavor jets. And in order to do that, we set up a neural network of our own, like a working GNN, which will reconstruct the secondary vertices inside a jet. Okay. And we established that this method has a better reconstruction efficiency of heavy flavor jets compared to a regular neural network. We published it, and also this became the mainstream tagger of Atlas. And this is a demonstration that DL1 kind of architectures are a fully connected network where you feed a jet and ask it to predict whether this is a heavy flavored jet, top, this kind of light flavored jet, etc. Versus when we apply this method we developed, which is called this GN1 and GN2. You don't need to know why 1 and 2, but this is just identifying the secondary vertices in a jet. This certainly gave us better performances. So this is a demonstration that if you really want to exploit the physics and do it through neural network by really learning the intermediate physics processes, that probably is going to give you a better understanding and interpretability and better performances. And that's being demonstrated here, okay? Just to show you some physics impact, we are applying it for Chamyukawa and applying these kinds of methods. Right now we have brought down the upper limit on Chamyukawa within touching distances, and we are pretty hopeful that upcoming LHC data is going to show this physics process. I mean, all the credit to the great neural networks which are under development. Some generative models, I have 5-ish minutes. So for generative models, what we try to do is to feed like a bunch of particles to a trained neural network and ask it just generate the calorimeter showers, because this kind of methods, the GN4 simulation is pretty much time taking. And this is right now like a bread and butter thing inside the big collaborations where they're trying to bypass the GN4 simulation and writing generative models which can do right kind of detector simulation. Some of the architectures, these are like permutation invariant generative models for calorimeter shower generation, as well as message passing based methods. Okay, and the real gain is that in computation time, where a GN4 takes like exponentially large times versus the particle energies, the forward computation times for a trained neural networks remains more or less unchanged, okay, and the performance goes down. So this is really a well motivated gain when we use generative models. I mean, given that particle flow is my personally favorite, we took up a project that why don't we write a generative model for particle flow themselves? Just bypass the whole GANT simulation and the reconstruction. What if we train a neural network where we will give a bunch of truth particles and it should give me a bunch of reconstructed particles? So this is a constraint set generation problem, and we are trying to improve it further. Okay, and there are some fancy architectures to be developed because it's not an easy task to get the right kind of fluctuations per event on the whole global level. So we are trying that, and we published this paper, but I think there are more to do in this direction. Right, so in last, say, 2 minutes or so, sorry, I have 4 minutes? Okay, so let's go through what's happening now, like what we should be excited about. I mean, each of us have our own opinion. We can be excited about it, anything, but let's say what's happening in our community right now. One major thrust is ongoing on the explanation side, because if we finally can't explain what these great trained neural networks are doing and what physics are they learning, then probably we can't extract the best out of these neural networks. One of the prescribed methods in the world of machine learning, I'm giving you a snapshot, an example of GNN explainers, because at least in the experimental side, GNN is the most like used architectures. This has been tried out, and we are trying to see that given a set-like construction and after the message passing happens, which nodes of a graph really correlates with each other in inferring a decision. Okay, and that has been applied in the MLPF project built by the CMS people, and they build up some R score to check which information propagates in a message passing network from one node to another, which edges got ignited, and to infer meaningful physics out of it. I haven't worked personally on this direction, but I'm excited with the progress which is happening in this way, and I'm looking forward to it. This is again another paper of feature correlation for top tagging. So feature propagation has also been studied to see, like, if a trained neural network say, okay, this is a like a jet with substructures, etc., etc., then what are the core physics parameters at the low level which it's learning? And people are venturing all possible feature correlations to understand that. And the most crucial question we, as a community, which we should answer is that in general, even if we apply Bayesian kind of networks, where it gives you a total uncertainty on the end, on the predicted observable, there are, in general, two kinds of uncertainties which are involved. One is called aleatoric, another is epistemic. The aleatoric ones are like, if you keep adding more and more features to the neural network, ultimately, if you keep adding correlated features, you're not feeding new information to a neural network. So your uncertainties on the predictions won't go down. Okay, so given an uncertainty estimation, how much is that uncertainty coming from the feature distribution? And then given like order of million parameters in a real life neural network, due to stochastic gradient descent learning, there will be uncertainties on those parameters itself. And those are like epistemic uncertainties. How much is the contribution due to those? This is something which we need to understand. And if we put a total uncertainty band coming from our systematics, we need to be able to correlate what is the physics-driven total uncertainty versus what is the ML uncertainty. And this is completely open question in which we should, as a community, probably should invest some time. And if you browse machine learning literature, this is a very nice review. It gives us all possible way from different mathematical angle how to compute uncertainties. But not all uncertainties will match with each other in terms of numerics. Probably a subset of them will catch the physics which we are interested in, but which one are really getting the right physics is something to investigate, and this is like an open problem. Okay. Some new directions which are developing. One is differential programming in high energy physics. I'm learning it myself, trying to apply for some project. But the whole idea is that if you can map a whole end-to-end learning program where each of the sub-pieces of the activities are differentiable with respect to each other, probably that can be used to optimize like a detector geometry and things like that. The whole experimental design optimization can be done through differentiable programming. And so in the theory direction, people are trying to write down matrix element generators, etc., using the same methods. This is something, a mad graph written in differentiable programming language JAX. Okay, so things are developing to keep an eye on. Not every number or result to believe, but nonetheless, it's an exciting development. Another direction which is exciting is like symmetry equivariant networks. So just from representation theory, if we recall back what are the definitions of symmetry equivariant functions, we can elevate the regular functions to parametric functions, which are neural networks, and can exploit them. So this is an example for boosted top tagging, where if you have the individual layers as Lorentz group equivariant layers, they somehow perform better for high boost regime versus the layers which don't exploit the Lorentz symmetry. So this is again something, another direction which is growing, and we are excited about it. On a realistic scenario, ML on FPGA is something to keep track of, because you need fast computation, and if you want to really design triggers at your L1 level, then probably reconstructing jets at low-level hardware on FPGA and making quick decision is a important task, and for that we really need to implement our ML-based architectures and compute them on field programmable gate array hardware. So this is a growing direction. There is a software package called HLS for ML, which can incorporate TensorFlow, PyTorch, all these software codes together and compute them on FPGA. It's exciting, surely. So let's see. I mean, my time is more or less up. So what's the takeaway? All I can tell you, and probably you will agree with me, that ML is here to stay with him. I mean, whatever you do, upcoming 10 years, unless some complete drastic thing happens, we are going to use machine learning. And when the tasks of an experimental design to the end experimental goal are written in terms of an ML language, then the big experiments, they're not much different. Conceptually, we are solving the similar kind of tasks. Okay, so we should probably talk with each other more. Need a keep close connection with the statistician and computer scientists. Like, they are really writing down fundamental mathematical components of deep neural networks, keeping a track of how much is the differentiability and things like that. We need to talk to them. There are other things like symmetry, equivariance and stuff which are ongoing, and probably they will help us. Now, one thing I really didn't want to talk about, there are a growing interest in quantum machine learning, but I see them as like adding few extra parameters. Maybe you know better, you have done some work probably in this direction, but we also need to see where this is going. And if it turns out to be fruitful, then why not incorporate them? So most of our papers and work are collected here in this GitHub page. If you really want to know, browse them. It has hundreds of papers, and everyone who publishes their results, the codes, they're all well tracked here. Okay, so hopefully we can keep exchanging with each other in future cases and see where the LHC community and EIC community goes and grows together in the context of machine learning. So thank you.
Thank you, Sanmay, for such a very nice talk. Time for questions.
No questions.
It was a very clear talk.
Or completely unclear in the dual space. But,
okay, I have a very naive question.
Sure.
I also don't know whether it is appropriate to ask, but machine learning is like training, right? Training a program. And
no,
train,
so,
yeah,
okay.
They're different, but when you're training, you train for some certain things. Do you expect something new to find out from the already trained certain things?
No, so probably this goes back to like the very initial slides, which let's concentrate on this slide. So when we say training and we are just injecting known stuff, you're talking about supervised learning, where you know what you're feeding the neural network, you know what's to expect. You ask a neural network, find that great function f, which should do this forward mapping. Okay. Now, if you're doing this on a real data, there are no labels. So there you have to take help of unsupervised learning and self-supervised learning, where you show the same object and say, I don't know what beast is lying in this data. You try to find the pattern and tell me what pattern you have found. And if you are after finding new physics and stuff like that, you probably better go for this unsupervised learning techniques.
Exactly. I mean, even if I forget about physics at the moment, I think about only mathematics. And the input I give from mathematics to ask them to learn these things, that also needs to be changed in that case. Like how it should learn.
I mean, how it should learn is encoded in the function and the loss function. Yeah. Okay, so you decide from your intuitions and knowledge, how do you want a nonlinear function to learn the data? Now, given the data is unlabeled, it's all up to how well it will learn, depends on how smartly you can design f and loss function. That's it.
Thanks a lot.
There's a question there.
Just a comment in case you're not already aware, there's an annual AI for EIC workshop.
I know that.
Yeah, okay, so if, to get more involved, that would be a natural place to get more involved if you were interested.
Yeah, sure, I saw the talks, what's happening there, etc. So Yeah, thank you.
If there are no other comments or questions, let's thank Sanmay again.
Okay.
And we'll reconvene at 2. Thank you.